So it's great to be back together again, and I'm glad you were all able to find this room. In fact, it's wonderful to be with thousands of members of the international physics community working together to advance physics for the benefit of humanity. And tonight, I'd like also to extend a special thanks and a special welcome to those joining us online, both in the United States and abroad. I'm excited by the many opportunities that are opened by the virtual component of this meeting. I'd also like to give a shout out to the many APS staff who are working behind the scenes to make this event the best it can possibly be. It's challenging enough to put on just one meeting of this scale and complexity, let alone two. This meeting wouldn't be possible without the dozens of APS staff who have dedicated their careers to the success of this organization. So I would like to thank them. We owe them a lot. So as Bob said, the past few years have been challenging, but fortunately, we physicists do know a thing or two about turbulence. And over the course of the pandemic, we have learned even more. And because of that learning, APS has emerged stronger and more resilient than ever before. We now have more ways to connect and more ways to build a welcoming and inclusive community. And for that, I am very grateful. And so now it's my pleasure to introduce the 2023 March Meeting Program Chair, Smitha Viveshwara. Smitha has been a stalwart partner to the APS meeting staff in putting together this event, and her passion for both science and art were driving forces behind tonight's exciting program. Please join me in welcoming Smitha to the stage.
Thank you, John, and a warm welcome to all of you. It's really been a joy and privilege to work with the APS meetings team and program committee in all their enormous efforts towards this March meeting. We have a fabulous mix of programming that I'm really excited to share with all the attendees here and who'll show up over the course of the coming days. It promises to be a combination of stimulating scientific sessions, as we all well know, and we're back full force, ample networking opportunities, and several special events, all of which you all are already bringing to life. As a launch, this evening, we now feature a March meeting tradition, the Kavli Foundation Special Symposium. For more than 20 years, the Kavli Foundation has shared APS's mission to advance science for the benefit of humanity. With their support, we're able to bring to you a diverse array of speakers that exemplify the contributions of physics to our understanding of our world and our universe in a multitude of ways. We also welcome you to join us immediately after the symposium for the world premiere of Cosmic Tumbles, Quantum Leaps, a production created for our APS March meeting especially, and performed by Nathalie Gaultier's youth group, Le Petit Cirque. The performance will pay tribute to the marvelous physics that you will see in this symposium and throughout the whole meeting, and it'll also bridge us to Las Vegas out there, through one of the city's major highlights, its incredible art scene, which draws some of the best performers in the world, as we well know. Turning now to today's featured Kavli Symposium, we take you on a journey exploring rich phenomena from the atomic to the astronomical. As we build up in physical scale, our fabulous speakers, globally recognized for their research and science communication, will lead us through the frontier physics to the realms, from the realms of ultra-cold atoms, quantum matter, our Earth, and finally our cosmos. And as a practical matter, at the end of each of these talks, we will have a short Q&A session as well. So now, let me introduce, in opening the Kavli session, we have Professor Monika Aidelsburger from the Ludwig-Maximilians-Universitaet, who studies the coldest states of matter in the universe. Monika is a leader in engineering and exploring a range of exciting physics in ultra-cold trapped atomic optical lattice systems. She's demonstrated remarkable quantum simulations of many-body phenomena that are of much interest to multiple communities. The phenomena include topological phases of matter, many-body localization, the alluring Hofstadter's butterfly, non-equilibrium dynamics, and even atom-by-atom manipulation. Today, she will share some of this exquisite physics. And with that, I welcome Monika to the stage.
Hello, everybody. Thank you so much for having me. It's a pleasure to be the first speaker in this symposium session. And I will be the one that starts with the smallest length scale, so from manipulating individual atoms. And then in the following talks, you will be taking to larger and larger length scales. The topic of my talk is quantum simulation. And before introducing our experimental platform, I would like to give you a brief motivation why we believe that quantum simulation is important and can contribute to the development of new technologies. So this is something that is familiar to all of you, the excitement about new quantum technologies that range from a large variety of different applications, starting from material science to communication, sensing, but also the hope of building more efficient quantum computing protocols. Now, I think the challenge with all of these applications is that we first have to understand how many interacting quantum particles work together. So we need to somehow understand their properties, and that's the challenge. So that's in some sense what we want to harness, but that's also the challenge that we need to face. And the main reason why this is so complicated is that if we have a large number of particles, then if you want to treat it exactly with classical computers, then the resources scale exponentially with the number of constituents. And so in order to solve this problem, there's one beautiful idea that is, instead of using classical computers in order to study these phenomena, we build a quantum system. We build a quantum simulator where the individual particles behave quantum mechanically in the way that we want. And the idea of analog quantum simulation is then to directly take a problem of interest, a model Hamiltonian, and implement these microscopic degrees of freedom directly in the lab. And there are many different platforms that work on that. Here's a selection of some of the most prominent ones. So they range from superconducting qubits to trapped ions, Rydberg atom arrays, and all of these will be explored and explained in different sessions during this conference as well. And we are working on the platform with neutral atoms in optical lattices. And what you see here on this lower right image is cesium atoms that are trapped in a square optical lattice. So each one of these individual bright blobs corresponds to one cesium atom that scatters a few thousand photons. And before I start explaining some of the things that we can do with this platform, I want to briefly show you how such a system actually works. So if you go to the lab and you want to set it up, there are several steps that you need to take in order to arrive at this image. And so let me share you a few pictures from our lab. So this is the cesium lab that we started building a couple of years ago, where I can explain the different steps that you need to take. So what you see here is an optical table with a vacuum chamber on top of it. And on the very right, you see some part that is wrapped in aluminum foil. So this is the atom source. There we put in 5 to 10 grams of material, then we heat it up, and these hot atoms diffuse into the vacuum system. And if you follow with your eyes from this aluminum foil part to the left, then you see that there's a steel tube, there are copper coils wrapped around it, so the atoms will actually diffuse into this vacuum system. But they are very hot. So for cesium, we heat the oven to about 90 degrees. For ytterbium, it would be more, it would be like 420 degrees. So we first need to get them cold in order to see any quantum phenomena. So the first step to slow them down is actually to shine in additional laser beam that is near resonant, and it compensates the Doppler shift. So the counterpropagating atoms, so photons and atoms are counterpropagating. By absorbing many photons, the atoms progressively get slowed down. So that's the first step for getting them to a lower velocity such that we can actually cool them further. And this happens in this first section of the chamber, that's a steel chamber. Here we build a laser cooling magneto-optical trap, where again, according to the Doppler shift, the atoms would be slowed down and cooled from all three directions. So all of this happens in a vacuum chamber where the pressure is on the order of 10 to the minus 8 to 10 to the minus 10 millibar. And all the cooling really happens only via the interaction with photons. But this is not yet cold enough. So we get to temperatures on the order of 10 to the minus 6 Kelvin, so on the order of a few microkelvin, but we want to get colder. And we also want to have a large optical access to actually see and manipulate the atoms. So what we do in order to achieve that is we move the atoms from one section to another. Now, at this point, the atoms are already quite cold. They are actually on a level of microkelvin. So what you can do is you can actually build traps out of light. This makes use of this AC Stark effect. So we use laser beams that are very far detuned from any internal transition. There's no absorption emission. It's only virtual mixing of states. And these traps can be on the order of millikelvin depth. So we can actually turn the laser beam on and trap the atoms in potential wells. So for instance, if we use two laser beams counterpropagating, this generates a periodic energy landscape for the atoms, and the atoms would accumulate in the minima of the potential. So now that's great. Now we have them in these little buckets. But since we apply this potential by interfering laser beams, we can manipulate it. So now if we detune the frequency of one of these two beams, this standing wave starts to move. And it will drag the atoms along with it. So it's really like a conveyor belt that in a few milliseconds takes the atoms from one chamber to the next. Now we end up in the final science chamber, and there we have even better vacuum conditions, 10 to the minus 11 millibar, and that's important because this determines the lifetime of our atoms in these traps. Now, the final science cell is actually hard to see in this image, so I have a zoom in. The final science cell is fully made of glass. It has these 11 side ports, and the top and bottom window are about 3 centimeters in diameter. So it's a very tiny cell. We can get very close to the atoms with optics, which is important in order to build a microscope. Now, in this final cell, we actually cool the atoms further down. In order to see quantum phenomena in the system to happen, we need to reach nanokelvin temperatures. So there's an evaporative cooling step in an optical trap, which allows us to cool the atoms below a critical temperature so that if we work with bosonic atoms, they form a Bose-Einstein condensate. And this is just a cartoon picture of how you may think about this Bose-Einstein condensate. It's essentially a macroscopic wave function, so 10 to the 6 particles can occupy the same energy eigenstate, which in this case would be the ground state of a harmonic trap. Now, we can also work with fermionic species. So in this case, the fermions, here's 2 spin components, would fill up all the energies until the Fermi energy. At this point, that's actually the lowest temperature that we reach in this experimental cycle. So from this point on, we try to be as adiabatic, as gentle as possible to the atoms and manipulate them in order to load them into the final trapping geometry. And in our case, this is mostly potential energy landscape that is generated by additional laser beams that interfere and generate lattice potentials. And just to highlight that already now, all the experimental data that I will be showing you today has been obtained with Bose-Einstein condensates, so with bosonic atoms. All right, so now we have this cold atomic cloud, which we can prepare in different potential energy landscapes in periodic potentials, so-called optical lattices. And here's again the simplest example of 2 interfering laser beams where the distance between neighboring wells is on the order of the wavelength of the light. Now this is the simplest geometry, but of course we can overlap many of these beams. And here's an example that I've taken from Uli Schneider's lab, where they have overlapped many different lattice potentials in order to generate a quasi-crystalline potential energy landscape. So this just to show you that by interfering them in different ways, you can engineer more complicated lattice Hamiltonians. So now, but let's just do the simplest one, which would be a square lattice. So we have 2 standing waves, 90 degrees with respect to each other. And again, here on the right, you see the image of the cesium atoms that are trapped in such a square lattice potential. If we do a good job and the atoms are actually cold enough, the dynamics is described by 2 simple parameters, which are here labeled by J and U. So this is the Bose-Hubbard model, where J determines the tunnel coupling between neighboring sites, and U is the Hubbard on-site interaction energy when more than one particle is on one site. So that's a paradigmatic condensed matter model Hamiltonian here for bosonic atoms, but we can also realize that for fermionic atoms. And this setting allows us then to study, for instance, the phase diagram of the Bose-Hubbard model. We can also load more internal states into the system. We can make these Hamiltonians more complicated, study spin models. But this is the basic underlying dynamics that describes the atoms in such a lattice potential. And what I want to explain a little bit more is how this system allows us to get complementary information about this condensed matter type Hamiltonians. So I already mentioned that in this image you can actually see individual cesium atoms. And the reason why that works is that the distance between neighboring sites is on the order of micron. It's on the order of the optical wavelengths, while in condensed matter you would have angstrom length scales. So what we do, here's another schematic drawing of the final science cell, is we have these atoms trapped in the lattice in the center of the glass cell, and then we can build high-resolution imaging objectives in order to collect light that is scattered by the atoms. So how the imaging process works is as follows. We first do the simulation, and then before taking the image, we make the lattices very deep, so that they are a few hundred microkelvin deep, and then we shine in near-resonant beams that scatter photons. We collect a few thousand photons per atom, but at the same time we need to cool. So there's an optimal configuration that allows us to do scattering and cooling at the same time. Oh, sorry, I don't know why this went back. And then you get images like that, where here you see a collection of cesium atoms, here in a very dilute configuration, so there are only a bunch of cesium atoms that you find on this image. But this allows us to also characterize the imaging properties, the resolution, the point spread function, and also the signal-to-noise ratio that we obtain from these atoms. So this is very powerful because we get these density snapshots, which allow us to study correlation functions, but also fluctuations in particle number that allow us to measure information spreading, for instance, in quench experiments. So since the first realization in 2009 and 2010 of these quantum gas microscopes, there has been a number of them. And this is just a small selection. So these experiments have been built with a selection of alkali atoms, rubidium, potassium, lithium, but also more complicated atoms like ytterbium. So the question is, what's the challenge in the field? Like, where do we want to go with this? All of this is very beautiful, but what is coming next? And some of the key challenges I try to summarize here. So what we actually want is to scale it up even further. We want to have more particles while keeping the control on the level of a single atom. And we want to have very accurate realizations of the model Hamiltonians in order to be able to actually make predictions that are useful for theory. And something that may not be so obvious is that there is actually always a harmonic confinement. Since the atoms are trapped in laser beams, they have a Gaussian profile, so there's an overall harmonic trapping potential that keeps the atoms in place. And it takes some additional techniques in order to get rid of that. And this is what I mean by large homogeneous systems. By that, I mean that they see a flat potential energy landscape. At the same time, we want to improve our fidelity for detection and state preparation. So we need to go to even lower temperatures, and there are several additional ideas in order to reach that, for instance, also for studying the ground state phase diagram in the Fermi-Hubbard model. And something that I will be focusing a bit more is to engineer new techniques that allow us to study new model Hamiltonians. So I've mentioned the Hubbard model, but there's of course a lot of other interesting model Hamiltonians that we may be interested in studying. Here is an image from our cesium quantum gas microscope, and I would like to motivate a little bit why we actually started to build this experiment. So this is a new quantum gas microscope with cesium atoms, and we chose it because it has more tools available for us in order to engineer novel model Hamiltonians. So for instance, interactions of these cesium atoms are tunable, and state-dependent potentials can be engineered with low heating. So this is a very large system of more than 2,000 atoms, and the filling is very high. It's on the order of 98%. So that's a very nice initial state for performing quantum simulation. But you also see that in this nice box, I've actually kind of cheated, if you wish, because you don't see the individual atoms. I promised you a quantum gas microscope, but if I ask you to count the number of atoms here, you will have a very hard time believing me that this is actually really more than 2,000 atoms. But we actually have a lot of information about this, so we can actually still work with it as a quantum gas microscope because we know the underlying lattice grid, we know the lattice constant, and we know the point spread function. So each individual atom that sits on a specific site would be convoluted with the point spread function that we can calibrate. So it's actually a deconvolution problem, which can be solved, but the experimental noise, the finite signal-to-noise ratio, can make that very challenging. However, in our experiment, we have managed to achieve very large signal-to-noise ratios, so we can actually reconstruct the density distribution of that image. And that's important because actually you see that in this case, atoms are bunched very closely together. The lattice spacing is only 380 nanometer, which pushes the energy scales up. The tunnel coupling is much larger between neighboring sites in short spacing lattices. And there are also a number of other reasons why short spacing lattices are actually interesting for quantum simulation. And how we solved this problem was actually with machine learning. So I just give you a very brief teaser of that. You can look up the details in the reference below. The idea is that you actually feed the experimental images of atoms in the lattice into a encoder-decoder network that then reconstructs the density distribution according to this bottleneck. So in essence, what this does is a dimensional reduction. You have this imaging information that you feed into the network, and you force it to reduce it to the lowest number of degrees of freedom, which means it is forced to tell you if a site is 0 or 1, if it's occupied or empty. And this actually allowed us to reconstruct our density distribution with very high fidelity. Now, there's one additional aspect that I wanted to mention, and it's some preliminary data that I would like to show with you, because the question is, how good is this quantum simulation? And I've emphasized that we actually want to have large, homogeneous systems that we can work with. And the first experiment that we did is to do a benchmarking of how well this potential actually is. So this can work as follows. So I mentioned to you that this quantum many-body system that we generate in the lab is actually in this glass cell, and it's completely isolated from the environment. So you can actually study fundamental questions about the thermalization of isolated quantum systems. And here we have prepared an initial state, which is a charged density wave, where every other site is occupied by one boson. So this is a highly excited state in a homogeneous lattice potential. We can generate it. It's a product Fock state. And then we can study its thermalization by suddenly turning on the tunnel coupling. And there's nothing special about this lattice, so we expect it to just thermalize. Okay, so this initial charge density wave should become completely washed out. But now with the quantum gas microscope, we can study more. We can study the spreading of correlations. So we can actually measure density-density correlations in the system. And what you see here is an evaluation, a measurement that we have performed in this homogeneous lattice, where we see very nice coherent spreading of density-density correlations over large distances of up to 18 lattice sites. And in order to be able to see that, of course, it's important that we do actually have access to such a large homogeneous system, which in our case here had 40 sites along the chain. And so this is a hardcore integrable model, but now we can, of course, go ahead and use the tunability of the Hubbard parameters in our system in order to study other systems as well. So we can study the transition to the chaotic regime, for instance. All right, so this is actually the experimental system that we have at hand. Now the question is, what can we actually simulate it with it? Okay, and here's actually one more picture that I forgot that I wanted to show you. You saw the half-empty table on the first slides. This is actually how it looks now. It's the same experimental table, now with a bunch of optics. They are all there in order to cool the atoms and actually trap them in lattice potentials. And the glass cell is somewhere hidden behind these yellow pillars. So actually these experiments, they become very complex, the more complex lattice model Hamiltonians you want to engineer. Okay, but let me go back to the question of what can we actually simulate. So there are Hubbard models, which is already nice because it allows us to study strongly correlated quantum matter. But there are a lot of other phenomena that we don't have access to directly. For instance, topological phases of matter. And the most prominent model that everybody knows is the integer quantum Hall effect. So let me just briefly remind you what it is about in order to explain in a bit more detail why it's challenging to realize and how we managed to do that in our lab. Okay, so what is the integer quantum Hall effect? You see here a Hall bar geometry. So if we have a two-dimensional electron gas in this system, and we send a current through the sample, we can measure transverse and longitudinal voltages. And in a classical regime, which is what you see now on the right, there's this linear relation between the magnetic flux that is applied perpendicular to the sample and the transverse Hall resistance that we measure. But now, as we crank up the magnetic field, and if the system is cold enough, then there are these plateaus that arise. So this is what is known as the integer quantum Hall effect, which can be understood in a single particle framework according to the topology of the energy bands. So what is so remarkable about these plateaus that appear in the spectrum is that they are given by integer numbers and natural constants. And these integer numbers, which are labeled here as I, it's actually the sum of all the integers that characterize the energy bands that are occupied with electrons. These integer numbers are determined by the topology and the geometric properties of the energy bands. And as you may know, this is of course very interesting for applications. If this is a very precise quantity, it's something that can be measured very precisely and can be compared between different labs and allows you to define a standard for resistance measurements. And this is also why it has found applications now in the redefinition of the SI units. So this is about the integer quantum Hall effect, which I mentioned to you can be explained or understood in a single particle framework based on the energy levels and the band structure of the electronic system. But there's much more to that. So there are, of course, many more interacting rich topological phases that would warrant being studied in a quantum simulation experiment. So this is basically the stepping stone for us in order to use the tunability of interactions and study interacting topological many-body systems. Okay, but you also see in this example that it may not be so easy to actually realize that with cold atoms, because what we have done here is looking at an electronic system and applying a magnetic field in order to break time reversal symmetry. If we do that in our charge-neutral atomic system, not much happens. If we apply a magnetic field, the energy levels split, there are Zeeman shifts, but there's no Lorentz-type behavior, so we wouldn't be able to see any of these phenomena. But because we generate these systems by hand in the lab, we can also manipulate them. And there's a technique called Floquet engineering, which essentially means that we periodically change the parameters of our Hamiltonian as a function of time. So we make the Hamiltonian time periodic, which allows us to engineer new effective Hamiltonian. And according to Floquet's theorem, that would be described by the evolution operator for one period of the drive, where we can introduce this new Hamiltonian HF, which can have topological properties. But there's a simpler way of seeing that. So in the high-frequency driving limit, you see some type of effective time-averaged Hamiltonian. So you all know this example of a saddle potential, which cannot trap particles, but if you start to rotate it at a certain frequency, the effective time-averaged potential that the particles see would be trapping in all two directions. And something similar can happen here. So you play around with the parameters, microscopic parameters of your Hamiltonian in order to engineer a new time-averaged Hamiltonian, which can then show these topological properties and allow you to study the integer quantum Hall effect, which we did by realizing the Hofstadter butterfly. Now, something that happens if you start with playing with time-periodic systems is that you have a quasi-energy spectrum. So due to this periodicity, the quasi-energy is only defined up to integer multiples of h bar omega. So if you engineer a two-band model, which is shown here in blue and orange, you actually have an infinite series of copies that are spaced by h bar omega. And this has important consequences for interacting periodically driven systems, but it's actually also a resource for studying new topological systems. And I want to have you keep that in mind, because we use it in order to engineer topological systems that actually do not have any static analog. But let me go back to this example of the integer quantum Hall system. I told you that the interesting part about the integer quantum Hall effect is this robustness of the plateau values that are defined by the topological numbers that characterize the energy bands. So we kind of thought, like, okay, can we do similar measurements with atoms, similar to the solid state example of a transport measurement? And indeed, that actually works. So if you prepare a cold atomic cloud in this energy band structure of non-trivial topology, and you apply a force to this atomic cloud, they will not move in the direction of the force, they will just be displaced sideways. And this sideways motion is linear in time, and follows the topological number, the integer, that characterizes the energy band. So you just get a linear displacement of the cloud, and from the slope you can fit the Chern number of the band, which in this case is 1. So this experimental value is very close to the theoretically expected one. And here I just want to briefly highlight something that is the basic idea of quantum simulation. So what you see here is a measurement or an artificial system that mimics a quantum Hall system, electronic systems in the presence of an artificial of a magnetic field. But this has been realized actually in a completely different setting. It's cold, charge-neutral bosonic atoms that are trapped in light. So it's a completely different realization that can allow you to study the same phenomena. And that's the basic principle. So whenever you have like an interesting many-body problem, you try to find the underlying Hamiltonian and implement that in the lab. And the techniques and the properties, the degrees of freedom can be completely different from the original system that you started out with. Now, having this control, I already mentioned that, we can start to engineer things that do not exist a priori in real systems. So we can try to engineer something where we don't yet know any analog. And this goes back to the idea of this periodic driving. We developed this technique based on the idea that we want to mimic integer or fractional quantum Hall systems. And what you know about integer quantum Hall systems is that once you know the topology of the system, the plateau value of the transverse Hall conductance, you also know that something interesting is happening on the edge. And it's enough to know the Chern numbers of the bands or the topological invariance of the bands in order to predict how many edge modes you would have at a topological interface or at the boundary of the system. So this is illustrated by these skipping orbits. So there's a direct connection between the two. Now in periodically driven systems, this is no longer the case, or at least not necessarily. Here I plot only one Fouquet-Brillouin zone. So there's still this infinite series of copies. It's a two-band model. And the red lines indicate the dispersion of edge states in a finite system. Now, what the bulk edge correspondence tells you is the number of edge modes leaving the band from the top minus the number entering from below is equal to the Chern number of the band. So if you do the simple calculation for this example here, you find 1 minus 1 is 0. So you have actually a system that seems to be topologically trivial, but nonetheless, there are topological boundary modes. And that's something that can only happen in a periodically driven systems because there's no notion of a true lowest energy band. You see that the edge mode can wrap around the Fouquet-Brillouin zone because this point, down here is equivalent to the one up here. So if you look at this edge mode, it wraps around this Fouquet energy mode. The way we realize this is by periodically driving a hexagonal optical lattice. Here you see 3 different instances of time, and the red bonds are increased in terms of hopping strength. Now, such a hexagonal lattice potential can be generated by interfering 3 laser beams under 120 degrees. If all the intensities are the same, it would realize a graphene-type lattice. So we would have a graphene-type dispersion. But if we imbalance the intensity of one of these 3 beams, we can enhance tunnel coupling along one specific bond. And now in order to realize this chiral modulation, the only thing that we need to do is to modulate the intensity of the beam as a function of time out of phase for the 3 different ones. And this is what is shown here. So we have this cosine type modulation of the intensity, which allows you to engineer this chiral modulation. And actually, if we drive the system very quickly at very high frequencies, this allows us to study conventional quantum Hall systems. It allows us to realize the Haldane model, while if we go to lower frequencies, it allows us to realize an anomalous Fouquet system where we have trivial Chern numbers equal to 0, but nonetheless topological edge modes. Okay, so I've talked a lot about topology and this connection to topological edge modes at the boundary of the system. But one important question is how to actually see topological edge modes in a cold atom system. And this brings us back to the question of harmonic trapping, because normally there's no interface. If you just have the laser beams and the harmonic confinement that keeps the cloud in place, you will not be able to have a sharp interface between 2 distinct topological systems. And in order to be able to actually realize these topological systems, we implemented an additional tweezer trap that allows us to confine the BEC locally in space. And we generate an interface, so we generate a repulsive wall with what is called a digital micromirror array. So this allows us to shape the intensity pattern. We make it dark on one half and bright on the other, and project it into the atom plane. So this is what generates vacuum. If you wish, in our case, we just apply a very large potential energy offset. And if we then move the wave packet close to this potential edge, we can try to get a good overlap with the edge mode at the edge of the system and study the chiral motion of the edge modes. And in our case, the width is like on the order of 2 to 3 lattice sites, so it's not infinitely sharp, but it's quite sharp. Okay, so let's follow the dynamics of the wave packet. It's off. But it's off. Okay. So the dashed line actually marks the edge of the system. We have our wave packet, so the particles can actually not propagate to the top half. So what we see if we follow the dynamics is actually that the wave packet expands and it follows this edge. And this depends on the chirality of the modulation or the chirality of the edge state. So if we turn it around, it goes to the opposite direction. And this becomes more apparent if we look at the difference image between the two. And of course, now we can also play with the shape of this edge. We can make a disk. We can make it go around the outside of a bucket. And we can turn the chirality. We can take the difference images. We can make straight lines. We can play with the sharpness of the edge. And there's a lot of interesting physics in that. And I want to highlight a talk by Christoph, who's a leading PhD student on an experiment that will give you more information on that. And so now I'm basically out of time. I just want to give you a brief outlook on what I think will be interesting in studying and where the field is going. So I've talked a lot about mimicking different lattice Hamiltonians, mimicking artificial magnetic fields by implementing these periodic driving techniques, for instance. But what is apparent is that we are only simulating part of the physics. The particles move around, but there are no actual fields. So if the particles move around, they don't have charges, so they wouldn't change the electric field environment. And this brings us to the topic of lattice gauge theories, which is much more general. So lattice gauge theories are characterized by the fundamental interaction, or characterize the fundamental interaction between particles and gauge fields, so fermionic particles that can move around in the lattice, between the sides of this lattice, and gauge fields that live on the links. So that's a very fundamental structure that actually is used to describe the fundamental interactions between particles in high energy physics, the low energy degrees of freedom of strongly correlated electron system. It plays a role for topological quantum computation, Nikita F-toric code. So having such a model system at hand, allowing us, or implementing such a model system would allow us to study and connect to all sorts of different physical phenomena that go way beyond condensed matter. Is it okay? And the challenge is actually that, okay, this model looks very similar, but it's actually not, because the local symmetries that we need in order to implement it is something that we do not naturally have. So it has this basic lattice structure, but main ingredients are missing. And this is easiest understood by looking at Gauss' law. If particles move, the fields need to change in a very specific way. And this happens locally in the lattice, so this is something that we do not have. But in the last few years, there have been many different proposals, many different implementations. This has been very exciting. And there are a few key steps that are still missing that we are trying to work on. So we want to go to 2D, and we want to implement it with fermionic atoms. And here, in order to achieve that, we want to combine what I told you about this nice lattice Hamiltonians, the global systems that we have at hand, with local control, which is provided by tweezer beams. So we want to be able to locally manipulate the motion of the atoms in the lattice in order to engineer the Gauss law. And we are going to implement that with the terbium atoms, which simplifies the complexity of the proposal, because we don't need two different species, bosonic and fermionic atoms, to implement these different degrees of freedom. We can work with a single species of atoms. And with that, I'm at the end. I just want to flash the slide. So of course, all this great work has been done by a number of great people. There was not enough space to put all the names. So if you want to know more, I just invite you to go to our website. So thank you very much for your attention. So yes, we can indeed track the motion of the particles. So in this case, it's actually a large number of particles because it's a Bose-Einstein condensate. So there are a few thousand atoms that we trap in one wave packet that move to the edge and then see it expand. And there's actually a lot more interesting physics that happens because it depends on the parameters of this initial state. What happens if it like extends into the bulk? If you move the edge away, you would see a beautiful hexagon emerge. But you can also track the motion of this edge mode, and you can create several. So you can also play around. You can create like a type of quantum point contact and make the wave packet split, go along two different paths, and yeah. 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 All right.
It's a general audience. Okay, I'm trying to flip the slides, but it's not working. All right, now, so I want to start by describing more generally, not just condensed matter, which is what I do, but in general, the fact that among the most fascinating states of matter that we have, that we know in the universe, are those where the interactions between the individual constituents are very strong. Okay? This is something that happens at all scales and in all areas of physics. For example, it happens in the quark gluon plasma, which is a state of matter that happens shortly after the Big Bang. Okay? And you have there quarks and gluons interacting very strongly. And nowadays we can recreate this in heavy ions collisions, such as those at Brookhaven National Laboratory. This is also something that happens in nuclear matter in neutron stars. Okay, this is a picture from the Chandra X-ray Observatory of a neutron star. And if you go to Wikipedia and you look at the type of phases that you have there, you have all kinds of phases of strongly interacting neutrons in these neutron stars, which are very complex, but which have very interesting names. And then, a bit closer to my field, to topological states, in condensed matter physics, when you have now electrons interacting very strongly among them, you have various topological states of matter. Okay, Monika has mentioned before, integer and fractional quantum Hall states, and these, again, can give rise to very exotic phases and very exotic properties, such as fractionalized charges or non-abelian statistics, etc. Now, if we zoom in a bit closer to the field of strongly correlated quantum materials, this is something where the electrons interact very strongly with each other, and this gives rise to exotic phases of matter. I just mentioned, for example, you have high temperature cuprate superconductors. Okay, so there are many materials classes that that exhibit these strong interacting phenomena, and perhaps the most famous is the high temperature cuprate superconductors. In that high temperature cuprate superconductors, in a phase diagram of temperature versus doping or density, we have a variety of phases, and we have very little understanding of these phases to this day. Okay, now one of the typical models, it has been actually mentioned already by Monika before, that is used to look at interacting electrons is the Hubbard model. Okay, and if you take, for example, a copper-oxygen plane, which is the basic unit that makes up high-temperature cuprate superconductors. You see, if you put 1 electron per copper atom, okay, that system is an insulator. It's called a correlated mode insulator. And now if you remove a few holes, if you remove a few electrons, you create a few holes in this lattice, electrons can now move from lattice side to lattice side. Before they couldn't move because the strong interactions between the electrons, they make them repel and they cannot jump because all of the sides are occupied. But if you remove a few of those electrons, now they can jump from side to side, and they do it in a correlated fashion that creates something pretty unique. It creates high temperature superconductivity. Yeah? Now, the simplest model that we believe captures the essence of this phenomenology is the Hubbard model, okay, where you have this energy repulsion U to occupy W one side, and then hopping energy T. Now, I said that we believe it captures the essential physics because we actually don't know how to go, from this model to this phase diagram, okay? It is extremely complicated, to calculate theoretically this model, even for the simplest, cases, and you have to use various assumptions, etc., and this, it's actually a very difficult task. Now, the difficulties, the complexity of calculating these things theoretically and understanding these models has led to alternative paradigms in order to investigate the physics of strongly correlated systems, okay? And one of those we just heard about is actually using ultra-cold atoms in optical lattices. Yeah? So I'll go quickly through this, as Monika already mentioned it, but basically you can shine, two lasers at each other and create a periodic potential. You can load atoms in this periodic potential, and they have exquisite control, the cold atoms community, over the parameters of their system, which means that they can tune, for example, the interaction strength. So already about 20 years ago, they were able to change between a mode insulator and a superfluid in the Bose-Hubbard model. This was done with bosonic atoms. A few years later, they were able to realize something similar with fermionic atoms, so to realize the Fermi-Hubbard model. And just to give you an idea of what is some of the latest that the community has been able to do in terms of simulations of the systems, so they've been able to realize antiferromagnetism in the Fermi-Hubbard model, several groups. So what you can see is this, quantum gas microscopes, and they can see that the spin of the electrons alternates up, down, over short length scales. So the cold atoms community is starting to explore this corner of the phase diagram of the Hubbard model. Okay, you can see both insulators, you can see antiferromagnetic states. They would like to explore the entire phase diagram, and in particular go down here to the region where you have D-wave superfluidity. But it is extremely challenging technically. Okay, as Monika mentioned, they are already at a temperature of about a nanokelvin or so, and they have to go down an order or two of magnitude in temperature, they believe, in order to reach this region. So we have traditionally these two platforms. One is actual quantum materials with lattice scales of a few angstroms, and where we don't have really too much control. And then we have ultra-cold atoms in optical lattices with typical length scales of the order of a micron, and where we have exquisite control over the parameters of the system. And what I want to tell you about today is about a new platform. It's called Moiré quantum matter, where the typical length scale this time is of the order of 10 nanometers. So it's nicely intermediate between these other two platforms and complementary. And we have not quite the same degree of control as in the cold atoms, but about a lot more than we typically have in regular quantum materials. Associated with these length scales are temperature or energy scales. Okay, so you heard already that in cold atoms, we're typically working at a nanokelvin or a fraction of a nanokelvin. In quantum materials, typical energy scales are of 100 or 1,000 Kelvin. In Moiré quantum matter, typical energy scales are 1 to 100 Kelvin, which is a very convenient temperature to explore in a solid-state physics laboratory. Now, initially, the development that enabled the investigation of this new platform, it's called sometimes twistronics, is the fact that with the advent of 2D materials, we can do something that we couldn't do before in the history of material science, which is we can put two two-dimensional materials on top of each other with an arbitrary angle of rotation between the two crystalline lattices. Yeah? I can choose an angle of 30 degrees, 20 degrees, 1.1 degrees, so I will show why not. Okay? And the electronic, optical, and mechanical properties of the system can change dramatically as a function of twist angle. It's a new tuning knob, something that didn't exist before in material science and condensed matter physics, but we can make use of it now with the advent of 2D materials. With this new platform, or quantum matter, okay, magic happens, and by magic I mean the following. We have been able to realize most of the phases, if not all, of condensed matter physics as we know them. We have correlated insulators, superconductivity, various topological phases, magnetism, nematicity, ferroelectricity, and the list goes on, strange metals, generalized Wigner crystals, acetonic insulators, Monika crystals. We basically realize in all of these phases with just a few ingredients, okay, as I will show you. And that is something which, has attracted the attention of a lot of people, and many people are working on. Okay, so with this introduction, this is what I actually want to tell you in the rest of my talk. I want to start by telling you a little bit about graphene and magic angle graphene, which is a little bit how it all started. Then I'll mention a few examples of what I call the rise of more quantum matter, what things which have been happening over the past few years. Then I'll just advertise a little bit the work that my students and postdocs are going to present in the March meeting, asymmetric, dual, and dual more quantum matter. And then I'll tell you a little bit about an outlook and how this more quantum matter community is actually impacting neighboring and other communities and what type of work is going on there, but just very briefly. Okay, so graphene and magic angle graphene. You have already actually heard about graphene and hexagonal boron nitride in the previous talk, which is great. So I'll just go very quickly. So graphene is a honeycomb of carbon atoms. It's one atom thick material, okay? All of these atoms are, from the chemical point of view, identical. They are all carbon. But from the crystallographic point of view, there are two types of atoms. We call them the A and B sublattices, or the red and green atoms here, okay? That is because you need two atoms in two dimensions to tile a honeycomb. Now, in a very simple quantum mechanical model, you can calculate the electronic structure, the energy versus momentum in the x and y direction for electrons in graphene. And it has this very unusual electronic structure, where near the Fermi level, you have these what are known as Dirac cones, or double Dirac cones, okay? You have energy versus momentum is linear in K, okay? That is the way ultra-relativistic, massless ultra-relativistic particles behave. Yeah? It's very different from usual electrons in solids, where you have typically a parabolic energy momentum dispersion. So if you, in fact, have a look at what is the Hamiltonian, the equation that governs the behavior of electrons in graphene, is nothing else but this equation, the Dirac equation, in two dimensions for massless particles. You can see here that we have energy is linear in momentum. I think this is the only equation in the entire talk, don't worry. But the next speaker told me I should mention graphene and the Dirac equation. So in the usual Dirac equation, you have here a spinor, which tells you whether the spin of the electron is up or down. Here, we have a pseudospinor, okay, a pseudospin, which is telling us whether the weight of the electron wave function is on the A type of atoms or on the B type of atoms. Okay? In addition to this, there is an extra degeneracy factor. We have two of these Dirac cones. They're called valleys, the K and the K prime valleys. So electrons in graphene have valley K prime, spin up and spin down, a fourfold degeneracy. Just remember number 4, it may appear later. So this is graphene, a single sheet. Now, what happens if you put graphene on top of graphene and you rotate the angle between the two lattices? Okay? A moire pattern forms where the moire wavelength, the distance between the soccer balls that you see here in the screen, is a function, is roughly inversely proportional to the twist angle, at least the small twist angles. Okay? So let me stop this before you get dizzy. So this is for graphene in real space. What happens in momentum space, and therefore what happens to the electronic structure? Yeah? I chose already the case when the angle is small, because I'm going to discuss small angles in the rest of my talk, for the majority of the talk. So if you have a small twist angle, you have the Dirac cone of one graphene sheet and the Dirac cone of the other graphene sheet. They're nearby each other in momentum space. So these are the two Dirac cones. Now, their separation is proportional to the twist angle for small angles. Okay? Now, this would be the situation that would occur if the electrons in one graphene sheet did not know that the other graphene sheet exists. However, because these two graphene sheets, when I put them on top of each other, are only a few angstroms apart, the electrons are very much aware that the other graphene sheet exists. In particular, they can tunnel between the two graphene sheets. Yeah? So that leads, at this point where the electron dispersions overlap, that leads to a gap opening due to this interlayer tunneling. Okay? This is the situation here depicted for the case when this interlayer tunneling is much smaller than the height of that crossing point. However, if I now change my twist angle towards smaller and smaller angles, these two Dirac points, these 2 points here, these two cones are going to get closer and closer and closer. And this gap opening here is going to be pushing one of these bands towards 0. Okay? So if I decrease the twist angle, at some point, when the interlayer tunneling is of the order of the energy of that crossing point, you push one band to 0. We say there that a flat band condition has been realized. Okay? And the angle for which it happens is called the magic angle. So the flat band condition is reached at the magic angle, and it's known and calculated to be 1.1 degrees for graphene on top of graphene. Okay? So this magic angle term was coined by Bistresser and McDonald, and there was also very interesting work by Eva and Ray experimentally looking with STM spectroscopy at Van Hoff singularities in the system that go towards 0 at that magic angle, and there was also earlier work by Suarez Morel also predicting these flat bands. So this is something which, is single particle physics, and, let's see what happens. So this flat band, before I show you some of the results, before I show you a cartoon, this is an actual calculation. Okay, so this is energy versus momentum. These are the flat bands. Okay, you see, we don't have now Dirac cones. We have these flat bands. Okay, these flat bands are not completely flat. They have a little bit of energy momentum dispersion, but that's just telling you that the real velocity of the electrons in the system is orders of magnitude smaller, okay, than when it was initially to start. Now, if you have a flat band in momentum space, if you want to go back to real space, okay, you have to do a Fourier transform. The Fourier transform of a flat thin is a highly peaked thin. So if you look in real space, where do the electrons in magic angle twisted layer graphene like to be? Okay, it turns out they like to sit in regions where locally all of the carbon atoms are on top of each other in the two layers. It's called the AA stacking region. Remember the A and B sublattices? So these are AA, everyone on top of each other. And then there is where the electrons like to be, and these regions are tunnel coupled by regions of where locally, due to the small twist angle, the atoms go out of registry, and those regions are called AB stacking, and the electrons do not like to be there. So from the top, and schematically, this is the way magic angle twisted layer graphene looks like. You have these regions of AA stacking where the electrons like to be, and then we have these regions of AB and BA stacking where the electrons do not like to be. In a slightly more realistic schematic, this is what we have. This is magic angle twisted layer graphene. The regions of AA stacking where the electrons like to be are spaced by about 13 nanometers. Okay? And this is going to form now the equivalent of the triangular Fermi-Hubbard lattice with cold atoms that we saw before. Okay? I put triangular in quotes because it's not really triangular, it's a honeycomb, okay, because the AB and BA regions are not the same. And I put Fermi-Hubbard in quotes also because this lattice has special topological properties in its electronic structure which prevent a direct mapping to the standard Fermi-Hubbard cold atom lattices. But you get the idea. You put electrons in these points, and it looks, and it works as a quantum simulator. So then what my group discovered in 2018 is that when you put electrons in magic angle twisted layer graphene, and now you can change the density of electrons, you can not only explore single particle physics, which was known to be there, but actually you can create correlated states of matter. Okay? And in particular, what we saw is that you can create special correlated insulated states, insulated states that happen because of interactions and that should not be present there in single particle physics. And if you tune your electron density around those correlated insulated states, you find superconductivity. This is all that happens only for angles around 1.1 degrees. Okay, so this is not only a superconductor, it's an electrically tunable superconductor, okay, where we can tune with electrons and holes and have superconducting domes. This is something that when I saw it immediately reminded me of the hundreds of times that I've seen phase diagrams like this, which are the phase diagram of the high temperature couplet superconductors. Let me flip the axis so that they correspond to exactly the same thing as here, where you can see that you have a correlated, in that case, motor insulator. And you do with electrons and holes, you get superconductivity, and something similar, but quite different in reality, happens here in the system. All right, so we discovered that thing, and we announced it, we posted and we announced it at the March meeting in 2018 here. And then, the theory tsunami came, this is just a short list of the papers that appear within a couple of weeks, of us posting our results, okay? All kinds of, the most important questions are what are the correlated insulators and what's the superconducting of the parameter, and all kinds of answers with all letters of the alphabet have been provided for this, S, P, D, D plus ID, F, everything, So basically, we don't know yet. There's a lot of people investigating. It's a very complex problem, okay? But we're getting some information, recently, which is quite interesting, and that I think other groups are going to share in this March meeting. Now, the popular press also became interested in this, and you started to have all these articles with super cool graphics. I wish I knew how to do these things, basically, this has created, a lot of attention. But more important, a lot of groups have started to work on this, both theory and experiment. I'm going to concentrate now on the experimental developments since the paper was published officially in April 2018. So the first thing that happened is that we have reproduced our own results many times. Believe it or not, that doesn't always happen, so it's good when you can reproduce yourself, okay? I heard somewhere something about a reproducibility crisis. We don't have it, at least in my lab. Now, many groups, better than you reproducing yourself is when other groups reproduce your work completely independently. Only then it becomes real science. And luckily, many, many groups have independently reproduced our results and extended them in many interesting directions and to other systems. We have discovered plenty of other phenomenology that is present in characteristic of quantum materials, such as strange metal behavior, nematicity, Fermi-Severide constructions, cascades of phase transitions, pseudo gaps, many other things. Okay, so we keep, finding out phases and finding interesting behavior in the systems. We have discovered many other correlated systems: ABC trilayer graphene aligned to HBN, magic angle twisted bilayer graphene, Moretti and this twisted monobi. There are plenty. Something which is extremely interesting is that, soon, about a year or two after our discovery, ferromagnetism, anomalous Hall, and even quantum anomalous Hall effect was discovered in these systems, which brought front and center the role of topology in these Moiré quantum matter systems. In fact, one of my pleasures, as in working in this field, is that this Moiré quantum matter has meant the merging of several condensed matter physics communities which did not interact that closely before. Okay? And these include, the 2D van der Waals materials and heterostructure, people did graphene, like me, and then the strongly correlated materials community, people that did cuprates, pnictides, heavy fermions, and then the people that did topological condensed matter physics, fractional, quantum Hall effect, topological insulators, Waals semi-metals. All of these three come together in this field of Moiré quantum matter, and that's really a great pleasure to interact with so many people now. Lots of local probe studies are giving us a lot of microscopic information about these Moiré systems. People do STM, scanning nanosquid, scanning ACT, scanning optical microscopy, scanning TEM, recently quantum twisting microscope. Let me just flash two very recent examples. One is STM work, super high resolution STM work from the group of Ali Yazdani, that you can see the images of these beautiful Moiré patterns, and then they can zoom in, they have atomic scale resolution over this broad field of view, and they can look at the wave functions actually in the various phases, correlated phases of the system. It's really phenomenal. And another example, one of my favorites, is the quantum twisting microscope. The group of Shah Halinani has invented this technique where they can put one graphene sheet at the tip of a microscope, another graphene sheet, and they put them together and they can rotate and explore, continuously as a function of rotation angle, the electronic properties of the system. This is, when I saw it, I was, wow. I thought it would take many more years to do that, but it's already happening. The last thing I will mention is that there is, we're building the next generations of Moiré quantum matter. And by that, I mean not just 2 layers, but, we call it Moiré Magic 3.0, 4.0, 5.0, because we can stack more and more layers on top of each other. So, a couple years ago, both my group and the group of Philip Kim, we had back-to-back papers in Nature and Science showing that if you take now 3 layers and choose the angles appropriately, were given to us actually by theory, you can realize magic angle twisted tri-layer graphene, which is an even stronger and more exotic superconductor than the bilayer counterpart. And just this past year, we decided to also try with 4 and 5 layers. So now we have actually superconductivity. The Moiré superconductors is a family of superconductors with at least 4 members, probably infinite, but we tried 4, okay? And this, this was done, also by, somehow papers appear in bunches, 2, 3 papers at a time in the archive, also by Stefan Nachpercha, by Emmanuel Tutuk. So this was actually very good. Now, let me say a few words about the work that my group members are going to present at the March meeting. They're going to be, an area of superconductivity and correlations in Moiré quasicrystals. I'm going to say a couple of words now, but I invite you to come Friday morning, session Y27, where Abiram, Sergio, and Tritep will do theory. We'll speak about this. And then also about correlation-driven quantum ratchets in a layer contrasting Moiré structure, work by Isaac Zheng. And I'm not going to talk about this, but I invite you also to come on Thursday to listen to Sue Chao talk about what happens when you have layer contrasting electronic structures also in graphene multilattices, in Moiré lattices. So just a couple of words about this. Most of the studies that have been done so far in Moiré quantum matter have looked at a single Moiré pattern, okay? That happens, for example, if you have a single twist angle, like, graphene on top of graphene, one angle, okay? In that case, you have a single Moiré pattern, okay? You can also look at alternating for multi-layers. You can look at layers where I put graphene, and then I rotate by theta, then by minus theta, then by theta. That's called alternating twisted multi-layer graphene. And that's where all the superconductivity has been seen. Because the system has special symmetries, theorists have told us there is a magic angle hierarchy with interesting topological behaviors, a tree of structures, and you can very nicely decompose this Hamiltonian into blocks, and the electronic structures are all easy to calculate and are beautiful flat bands plus Dirac bands, etc. It's all great and doable because of that single angle, single Moiré pattern. But in principle, even with a single Moiré pattern, when you put graphene on top of graphene, you don't have a Moiré, you don't have a periodic system. You actually have an atomic quasi-crystal. Okay, a quasi-periodic crystal, because the angles that you choose are not in general commensurate. The pattern never repeats itself. However, electrons at the experimentally accessible energies that we have in the lab don't see that atomic crystalline lattices. What they see is this Moiré periodic crystal. They see that supermodulation, which actually happens to be periodic. Okay? And that's why we can plot those nice bands, which look like if the system was periodic and it was a regular solid. However, what happens if instead of having one Moiré pattern or one twist angle, you have 2, okay? And the angles are not the same, okay? So if you have, 2 angles, theta 1, 2, and theta 2, 3, for example, if you have 3 layers, now the following hierarchy appears of length scales. At the atomic level, you still have a quasi-crystal. In fact, it's a quasi-crystal of rank 6, because you need 6 vectors to tile that real space. However, now you have you have 2 angles, theta 1, 2, and theta 2, 3, which means 2 Moiré wavelengths, lambda 1, 2, and lambda 2, 3. And if those Moiré wavelengths are not identical, which if the angles are not the same, they will not be, now you have Moiré patterns which are incommensurate. So you create something which is called a Moiré quasi-crystal. The quasi-periodicity is actually in the Moiré pattern itself, okay, rather than in the atomic scale. Ultimately, there is a Moiré of Moiré periodic crystal lattice at much larger length scales, but that is at an energy which you don't care, you can't resolve experimentally, okay? So the interesting regime is that, where we have a Moiré quasi-crystal. And then you can, of course, play with this. You can plot, what type of behavior you're going to have, so theta 1, 2 versus theta 2, 3. Magic angle graphene is a single angle there. Magic angle twisted trilayer graphene, the alternating one, is on that axis where the angles are the same, okay, theta and minus theta. I'm going to talk about when you deviate from that line, that now you don't have identical angles. Okay? So we realize this by placing 3 layers of graphene on top of each other and choosing alternating angles but not identical. Okay? And we have a dual gate geometry structure so that you have metallic plates here so that you can control the charge density and the displacement field and create asymmetries in the system electronically. Everything is controlled electronically. And this is what the device looks like. So when you do this, and you measure the resistance versus displacement field and versus total density in the system, you can see this complex pattern, which is kind of anti-symmetric, okay? If you apply displacement field in one direction, you polarize electrons and holes. You polarize in the opposite direction, you do holes and electrons, okay? And this allows us automatically, these type of features here allows us to measure what are the twist angles. We know that in this quasi-periodic crystal, we have 3 layers, but we can tune the density and displacement field such that we mostly occupy 2 of them. The other one is unoccupied. And then we can extract an angle from there. It's 1.4 degrees, 1.2. And if we do the same thing with an opposite displacement field, we get minus 1.9 degrees. So now we know that it's not 1.4 minus 1.4, it's 1.4 minus 1.9. They're not identical, so we expect this quasi-periodicity to appear. So what we can do then is we can apply a small magnetic field of 1 Tesla, and then you see all these beautiful patterns of lines here, crisscross. If I zoom in, there are like thousands of lines in there. These are Landau levels because it's an extremely high-quality crystalline system. Now, Landau levels appear in regular solids in periodic systems. So they appear here. Okay, this is periodic-like. However, there are regions where the Landau levels disappear. Those regions are actually the quasi-periodic ones. In fact, our theory colleagues have calculated what is the electronic structure of the systems, energy versus momentum. And it turns out that there are regions where features are periodic-like, you see these sharp bands, and then regions where you have a spaghetti of flat bands, which are quasi-periodic. Okay? There is where the quasi-periodicity, the quasi-crystal aspect, happens. It turns out you can actually measure correlations, flavor symmetry breaking phase transitions due to Coulomb interaction in the system, and you can measure superconductivity in the system, and all of that is happening actually in the quasi-periodic region, in the quasi-crystalline region. Yeah? So with this, I want to end this part. If you want to learn more, just go to this talk, and just a couple words about these correlation-driven quantum ratchets. Okay? So now we are going to create another asymmetric moire pattern, another system. But what we're doing is we take bilayer graphene, Bernal bilayer graphene, 0 angle between them, and then we're going to put top hexagonal boron nitride, which is an insulator, roughly with 0 degrees with respect to it, and then a bottom hexagonal boron nitride with a large angle, 15 degrees, 30 degrees with respect to it. We have 2 moire patterns, but vastly different. The 0 degrees one creates a long wavelength moire pattern here. The bottom one creates a very short moire wavelength pattern, which is almost invisible to the electrons, so the electrons just behave as if they were just itinerant. With this, we call this a layer contrasting moire structure. We again have metallic plates so that we can control the wave function, and send it to one layer or to the other. Okay? And this is a picture of how we do this thing. And then it turns out, if you take regular graphene without these moire patterns that I told you about, and you measure the resistance as a function of this top gate and back gate, you have a straight line with an angle given by the ratio of the capacitances to the top and bottom plate electrodes. That's the usual behavior of bilayer graphene. If we have, however, these layer contrasting moire patterns, this is what you see. You have this angle with a line, and then in the middle, it's vertical. In the middle, it's like we're changing the top gate voltage, but the electrons is doing nothing to the electrons. This is very odd. You may think, is this an artifact? No, it's not an artifact at all. We can see it and engineer it and do it many times. Okay? So this is something that leads to a very unconventional type of ferroelectricity, and it leads also to the quantum ratchet behavior that I'm going to mention. So if you measure the whole density in the system, you can see that across, by sweeping the back gate, the whole density, which tells you the carrier population of the system, has some slope, normal. If you measure it, however, as a function of top gate voltage, you see that in the middle, the whole density is not changing. The number of carriers in the system is not changing, even though I'm applying an electric field. That's consistent with this behavior not changing, even though I'm applying an electric field. Okay? Well, the way we know now that this happens, okay, and I'm going a little bit fast, please go to my student's talk because I'm running out of time. We know that the system consists of two types of carriers, some which are mobile and they conduct electricity, and some which are localized. Okay? These localized carriers, we can calculate how many of them are there and in which regime they appear, etc. Okay? And these localized chargers are basically in the top Moiré interface, the one with the long Moiré wavelength that tends to localize carriers. Whereas at the bottom Moiré interface, you have those itinerant carriers that can flow freely. Okay? This leads to a behavior where, again, I'm going to go very quickly through this. If you measure your Hall density, you measure a ratcheting behavior. If you apply the top gate voltage in one direction, the Hall density changes. If you reverse, it doesn't change. You apply it back forward, it changes, then it doesn't change. Changes, it doesn't change. This is a ratcheting behavior. You can do it for electrons or for holes, okay? And it's very unusual. It just means that the system is shuffling charge between the localized and the itinerant carriers, but in an irreversible way, analogous to a ratchet that you can rotate only one direction but not on the other. This thing can lead to very unusual things, like, for example, two-dimensional Moiré ferroelectric superconductivity and other things. Okay? With this, I want to end with the outlook. So you can see that we've realized all of this magic with these heterostructures. This we did only with graphene and a few other materials. We have hundreds of these 2D materials, so we can do this with many, many more structures and systems. For example, twisting Cooper superconductors, twisting to the magnets, etc. And beyond the condensed matter community, something that is happening is that people are doing this already with cold atoms. For example, this is a theory and experiment, realizing twisted Moiré systems with cold atoms. People are doing this with phonons and with classical vibrating plates. People are doing this with photonic lattices. This is actually a huge program with major Department of Defense investment in this direction because you can slow light tremendously. People are doing this also for electrochemistry and catalysis. And the latest, even gravity, people think you can do something. I don't know. We'll see. With this, I want to thank my students and postdocs, my group members, my collaborators, and I want to thank you all for your attention.
So, questions again, please. This time, someone come up to the mic, or I think you can raise your hands too. Go ahead, please.
Can you say in the question of this incommensurate superlattices that you create, is there also a notion of magic angle to see superconductivity and correlated behavior in this region? Do you need to tune to some angle or it?
Very good. So actually, you can vary the angle vastly. And what the electronic structure calculations suggest is that the dispersive part can get very stiff, but the quasicrystalline part often forms these spaghetti-like looking flat bands. And it's in those flat bands, even though they're not real periodic bands, but they're quasi-bands that we're able to realize by putting our Fermi level there, correlations and superconductivity. It would be very interesting to see the predictions, tell you that some angles are still more interesting than others. For example, it's very cool to look at the chiral structures in the same direction, where interesting things happen also. So I think we need a lot more theory.
Thank you.
Okay, wonderful. We have a couple, so maybe this side.
Hello, my name's Arturo Andujo from the University of Texas, El Paso. I wanted to ask a couple of questions. You mentioned that you observed magnetism. So my question is if those angles are different from the 1.1 degree, and if those are harder to achieve and as well studied. And finally, if you've ever observed magnetic moment tunneling from one graphene sheet to the next.
What tunneling, sorry, the last part?
A magnetic moment, maybe, from a graphene sheet.
Very good. So indeed, ferromagnetism has been observed. This was for magic angle graphene, so 1.1 degree, where one side was partly aligned to hexagonal boron nitride. Okay? So that induces a breaking of symmetry, which is important to recreate, to realize a special type of magnetism. Yeah? Since then, it has also been observed in several other Moiré quantum heterostructures. Okay, so it's a phenomenon which is quite ubiquitous when you have these interactions. We have not, to the best of my knowledge, this tunneling of the magnetization has not been seen, between Moiré heterostructures.
Thank you.
Great. So I think. Oh, sorry. Go ahead, Pablo.
Oh, there was just one there.
Go ahead. And then we'll have a virtual and then one last one, and that'll end the Q&A.
Wonderful talk, thank you. You started your talk by comparing to some of the results from the first presentation, which was also lovely. One of the strengths of the cold atom and quantum simulator systems based on AMO is studying dynamics. Can you comment on your access to any kind of dynamical signatures or phenomena, particularly entangled dynamics within Moria materials?
Very good questions. So, Floquet engineering has already been done also for topological phases in the solid state. My colleague Nugedic did it maybe about 7-8 years ago. So that technique has been already applied, in this case to the surface states of a topological insulator. There's nothing that prevents applying those techniques to Moire systems also, to realize, for example, Floquet engineering. So definitely there is access to dynamics in various ways. This field is quite new and the community is quite different, the one that does Moire quantum matter and the one that does those things. So I think it will take a little bit of time to apply those techniques to the systems, but it's definitely doable.
Thank you.
For the virtual.
Yeah, we have a question that says, when looking for flat bands, what determines if a band is flat enough in quotations?
Excellent question. So when I say something is flat, well, it's flat with respect to what, okay? So the thing that one needs to compare is what is the kinetic energy of the electrons compared to the interaction energy of the electrons. So when they become of the same order, okay, then interaction effects acquire a disproportionately strong role, and that's what leads to competing phases, many body states, and there are several of them, and they can be quite close in energy. Ideally, I mean, if you want to suppress completely the kinetic energy, then it's all interactions. Okay? But I think it's a very interesting interplay when these are comparable, or interaction just a little bit stronger, but you still have a little bit of kinetic, because that provides a lot of playground.
Great, thank you. And then one last question.
Thank you very much for your very inspirational talk. I'm pretty curious, so what motivates your group to test how many layers to test with, and also how many, what angles to twist?
Very good. So, well, the motivation is me telling the students we should do it. No, I'm kidding. There was this very interesting theoretical predictions by the group of Aspin Viswanath at Harvard, saying that, oh, I think the same thing that you did with 2 layers, you can do it with 3, 4, 5, in fact, infinite number of layers. And they should give you also flat bands. So the key question was, is magic angle twisted bilayer graphene an exception, and there's nothing else like it? Or actually, we followed that recipe of engineering flat bands, can we get additional superconductors and correlated states, etc.? So that was the motivation to study this. And thankfully, my great and very patient students and hardworking students and postdocs took up the challenge, because it's not easy to make so many layers. And indeed, we saw that no matter how many layers we did, the superconductivity is present, correlated states are present. If anything, it gets more interesting. So that was, really, it was not obvious that it was going to work out, but it did. So it was really great.
Thank you. That sounds very exciting. Thank you.
Thank you. So let's thank Pablo again for this lovely talk. And now we progress to the scale of our precious Earth, and we have Professor Brad Marston from Brown University, who has pioneered unique approaches to addressing challenging problems in our terrestrial realm. Brad studies and combines his understanding of quantum matter, fluids, and planetary atmospheres in very creative and insightful ways. In his recent investigations, he has applied wisdom acquired over decades on topological matter, some of which you saw here today, in the condensed matter realm, to his long-term research of fluid aspects of the climate system. Here, we will hear about the surprises emerging from this kind of cross-disciplinary exploration, potentially ubiquitous from the lab setting to the solar system and beyond. So with that, Brad, please. Sorry, can someone turn that mic on, please, there? can.
Thanks. It's a real honor to speak to you here today about the work that my collaborators and students and I have been doing. The previous two speakers told you about various states of quantum matter, and what we're going to see in a moment is that many of these same features are actually present in the Earth's climate system, and that there's a surprising connection between the fluid dynamics of Earth and the quantum Hall effect. And in some sense, we're in fact living inside of a topological insulator. Let's see, can I have my slides, please? Great. Okay, they're not advancing. There we go. Okay, I'd like to begin with a quote from Richard Feynman from the Feynman Lectures on Physics, and where he observed, "The next great era of awakening of the human intellect may well produce a method of understanding the qualitative content of equations. Today we cannot. Today we cannot see that the water flow equations contain such things as the Barber pole structure of turbulence that one sees between rotating cylinders." He's thinking about Couette flow here. Today we cannot see whether Schrödinger's equation contains frogs, musical composers, or morality, or whether it does not. So the work I want to describe is a small step in the direction of seeing the qualitative content of equations, in this case, classical equations, but as I mentioned, with some surprising connections to quantum physics. So the main theme is that topology turns complicated problems into simple ones. So the outline is as follows. I want to tell you about the El Nino and Kelvin waves in the climate system, and some observations and simulations, the physics of broken discrete symmetries, and briefly review the quantum Hall effect, although Monika already covered the things that I want to say about that. Then shallow water equations, which, as we'll see, have many of the features that Pablo described in a completely different context. Well, that will bring us to topology and winding number. And slides have disappeared again. All right, let's go through here. We'll look at some actual observations of the stratosphere and find topological signatures from those observations, and talk about topological waves in a magnetized plasma. So this is a view of the Pacific Ocean, and the colors indicate the height of the ocean, the anomaly in its height. The scale is just on the order of plus or minus 20 centimeters. So this comes from laser altimetry of the height of the ocean. And if I set this into motion, then what we can see is that there is an eastward propagating wave traveling along the equator of the Earth. And this is the Kelvin wave, and it's intimately connected with the phenomena of El Nino, which happens when a pool of warm water forms off of the coast of South America, having worldwide effects on the climate, as indicated in this diagram. So back when I was a graduate student, I noticed that there were strong correlations between the temperature of the Earth, especially in the equatorial regions, and the carbon dioxide content, the fluctuations in the carbon dioxide content in the atmosphere. This wasn't the greenhouse effect, because this was occurring over shorter time scales of a few years. Most of these temperature fluctuations were due to the El Nino, and the El Nino couples to the biosphere of the Earth in various ways, for example, through forest fires in the Amazon, leading to a positive feedback where in warm years, anomalously warm years, there's more carbon added to the atmosphere in addition to the carbon that we're adding as human beings. And so this El Nino turns out to be the largest climate oscillation on sort of human timescales. So let's look more closely at these waves. And to do that, I wanted to show you a simulation of a very simple fluid model, a two-layer model where I have a heavier layer of fluid underneath a lighter layer. And the force of gravity is acting as a restoring force to try to push down, in this case, this bulge of fluid, of the heavier fluid. And that results in a gravity wave that emanates out from a point of disturbance. So just as you would drop a rock in a pond, that would cause surface waves. And because this is on a sphere, if we look at it, here we go, on a cylindrical projection, we can see that the wave goes to the antipode and then comes back again, something that happened recently with the Tonga explosion of that volcano in the Pacific. Now, if I turn on the Coriolis force, then there's an additional restoring force, and the wave is no longer spreading out throughout the sphere, but is confined to the equator. There's a horizontal confining force that is basically making the equator like a waveguide, and that's the Kelvin wave. And you can see that it's non-dispersive because this pulse is maintaining its shape as it goes around. There's a second wave called the Yanai wave that is anti-symmetric with respect to the equator, and you can see that it is actually dispersing. The phase velocity and the group velocity are not the same, so you see this kind of phasing, and those two waves are going to play a central role in what I have to tell you. So if you want to try your hand at creating your own waves, I have an app on the Mac App Store you can download for free. It's called GCM, and I use that for both my research, but also as a teaching tool, and you're welcome to give it a try if you have a Mac. So now I want to tell you a little bit about discrete symmetries, and in particular, the CPT theorem. So let's consider the case of a rotating planet. Rotating planet breaks time reversal symmetry due to that rotation. And if we look at the planet in a mirror, then the mirror image reverses the direction of rotation. So the combination of parity and time reversal leaves the system invariant. Here, we're just talking about a neutral fluid, so C isn't playing a role, the charge conjugation. And we can think about this in terms of the Coriolis force. So the acceleration in a rotating frame, a non-inertial frame, is given by not just F over m from Newton's law, but also includes a term that involves the rotation angular rate omega crossed into the velocity plus a centrifugal force. And if we change the sign of time, then the acceleration remains unchanged because there's two time derivatives, but the velocity changes sign. And so in order to restore the form of the equations, we also have to change the sign of omega. And in general, it's the horizontal component of omega that's most important in the atmosphere, because that's most of the motion in the fluid atmosphere and oceans is in the horizontal. So we're looking at the vertical component of omega, and that's the Coriolis parameter, and it changes sign across the equator. So the equator is a boundary between two hemispheres that break time reversal symmetry in an opposite sense. So I don't have to tell you that the presence of time reversal symmetry breaking can have dramatic effects, and we just heard about the quantum Hall effect as a nice example of that. And in particular, the 2016 Nobel Prize recognized the work of David Thales in providing a topological explanation for the quantization of those plateaus. And we have this mechanistic understanding of that in terms of edge modes propagating along our semiconducting material. We see these half-circle orbits on the edges that are chirally moving in one direction, and therefore offering some protection from backscattering due to impurities. Now let's look at the shallow water equations, which is a highly simplified model of a fluid in which we have stratification. This heavier fluid is beneath the lighter fluid, as we saw in the simulations. The equations of motion have two pieces. One basically represents the conservation of mass, and the other F equals ma. So the top equation is telling us that the height of the fluid changes depending on whether there's a confluence or divergence of the fluid in the horizontal. That's the conservation of mass. And then down below, we see the effects of gravity in the gradient of h. That's the restoring force of gravity, and also the Coriolis parameter, the horizontal deflection. So we're going to take a closer look at these equations now. And to do that, we'll linearize them. We'll assume that we have relatively small wave amplitudes, and that the height of the wave, or the depth of the bottom fluid, is approximately constant, capital H. So if we look at the normal modes of that equation, then we have to diagonalize a 3x3 matrix in wave vector space, and we get a dispersion that looks a lot like the dispersions that we saw in Pablo's talk. There's a perfectly flat band, and then a positive and negative frequency band that are gapped away from that flat band by the Coriolis frequency. So that flat band is basically just what we call geostrophic balance. There's a balance between the pressure gradient and the Coriolis force. If we look at the wave functions, though, we'll notice something quite dramatic. And this keeps advancing. Can we go? All right. I'm not sure what's happening here. Okay. Keep on going, please. Okay, stop. Oh. Okay, good. So the normal mode wave function here in the lower left corner shows a singularity as we go around in wave vector space. Its phase changes by 2 pi, and that's going to play a central role in what follows. So let's now look at what happens as we study these shallow water equations while varying the Coriolis parameter f, going from the North Pole where it's positive to the South Pole where it's negative, crossing through the equator. So there's the gapped spectrum at the North Pole, and at the South Pole there's a gapped spectrum. But I've colored the bands in an opposite sense because there's a band inversion that's going on that we'll see in just a moment. Right at the equator, there is a Weyl singularity where the degeneracy, the gap vanishes, and we have this degenerate point right at k = 0. So we can compute a gauge invariant winding number and plot that as a function of wave vector. And what we'll see is that we have this singularity in the phase at the point k = 0. We have a winding number 1 vortex, and at the South Pole there's a winding number -1 vortex. So there's a switch from an anti-vortex to a vortex. The winding number changes by 2, and from the bulk interface correspondence that we already heard about, that means that there are going to be 2 boundary modes, and those 2 boundary modes are the Kelvin and Unai waves. So up here at high latitudes, we're in this gap regime, and that's the sense in which we're living inside of a topological insulator. Now, we can look at the spectrum of those waves near the equator. And so there's our Earth where F is changing sign across the equator. The spectrum was worked out by geophysicists back in the 1960s, and you can see here that there is these 2 waves, the Unai wave and Kelvin wave, spanning across the gap. They worked it out by directly solving the wave equation, but they realized that there was something that was not understood, something mysterious about it. And one of them observed, the question of why the equator supports a unidirectional wave, the Kelvin wave, is interesting scientifically and important mathematically. I have asked the question myself and been unsatisfied with my own answer, as well as the answer of other atmospheric and oceanic scientists. So this topological explanation now offers an answer to that, why there are these 2 unique waves that cross the dispersion. So let's see if we can observe this dispersion. And one way we can do that is by looking at satellite observations of clouds across the Pacific, which track this warm pool of water that moves across the Pacific as the Kelvin wave moves, because the warm water stimulates cloud formation. So if we look at the power spectrum of that, of the light being reflected back out to space from these clouds, then we'll see something quite interesting. First, let me remind you that this kind of experiment has been done in solid state physics for some time in angle-resolved photoemission experiments, where in this topological insulator, we see these 2 bands that are traversing a gapped region. So there is our shallow water dispersion. What does nature tell us? So back in actually the early 2000s, before there were any, I think, angle-resolved photoemission experiments, then the Kelvin wave and the Unai wave were both seen from these observations of the cloud brightness over the Pacific Ocean. So in the left lower panel, you see the power spectrum from the Kelvin waves, and then the right, we see the Unai waves. So that's the dispersion, but what about the more topological aspect, the winding number? Can we get to that directly? And the answer is yes. We can calculate this winding number from observations by looking at the observations of winds in the stratosphere, which is a particularly, as its name implies, a particularly stratified region of the Earth's atmosphere. And if we look at the winding number in a theory picture, then we can see that these gravity waves have a non-zero winding number, whereas the low-frequency geostrophic waves or Rossby waves do not. But what do the actual data show? So up in the stratosphere, there are a lot of gravity waves, and they're responsible for this amazing oscillation called the quasi-biennial oscillation that occurs with a period of about 26 months in which winds in the equatorial region of the stratosphere reverse, backwards and forth. Very striking. It's interesting that it's not 2 years, it's 26 months, and it's interesting how periodic it is because so few phenomena in the climate system are so regular. So there's lots of gravity waves, and when we calculate the winding number, we find down at the higher frequencies, the lower panels there on the right, that there is a non-zero winding number. The winding number is 1, as we expect from our theoretical observations, for theoretical considerations. So the observations seem to support this topological signature of our gravity waves. Now, if we look at a classic textbook on geophysical fluid dynamics, we can open it up and we'll find diagrams like this. We show that to a condensed matter physicist, they'll immediately recognize this kind of figure. And in fact, we've already seen this tonight. But the geophysicists have been working with this since the 60s, as I mentioned, actually even earlier, because this goes all the way back to Kelvin, who originally found this in the context of coastal Kelvin waves. So recently, Vinay and Delplace have shown that this topological analysis applies to the coastal Kelvin waves. And go forward. We can do an experiment with a tank of fluid. On the left-hand side is a non-rotating tank, and if we generate some waves, those waves will just emanate and go throughout the entire region. But on the right-hand side, the tank is rotating, the camera's moving with it, and you can see that these coastal Kelvin waves are traveling along the boundary of that tank. This is the paper from 1879 by Kelvin, and it's very readable. If we look inside, then here's his equation 15. We have an exponentially trapped boundary mode, which we can now recognize as the first topological wave in the literature, a century before it was rediscovered in the context of quantum matter. There are other oscillations in the Earth system. The Madden-Julian oscillation is one that we still don't understand very well, and it travels along the equator. It is a region of rain, and that is concentrated at the equator, that's red, and it may have a topological explanation. I don't know, but this seems like a likely candidate. The French group has identified topological modes of oscillation in stars. So going beyond the Earth now, there are predictions of modes that could possibly be seen in helioseismometry or astroseismometry, looking at the oscillations of the surface of the star. We've been investigating modes of topological modes in magnetized gaseous plasmas. This is a view of the Large Plasma device at UCLA, and when the pink coils are energized, they produce an axial magnetic field, and we predict that there will be a wave traversing a gap region that travels along the edge of the plasma in this device. And we've been looking for this experimental signatures of this wave recently there. This is, there we see the GPP indicates the gap, the mode crossing through the gap that travels along the edge of the plasma. And since plasmas are found throughout the universe in conjunction with magnetic fields, it seems likely that there's topological physics yet to be explored in that context. And this is just a view of the large plasma device, emphasizing that a lot of this physics can be done at a large scale, and where one can literally insert probes into the plasma. You see this flash of light is the plasma, and measure the density of the plasma, pick up electromagnetic waves, and so on. So, a few years ago, Nature magazine had an article, "Physicist, Your Planet Needs You." And this was in the context of cloud physics, one of the most challenging problems in the climate system. And the article argued that physicists have some unique insights that could contribute to advancing the understanding of the climate system. The APS has a topical group on the physics of climate, and they have a number of sessions beginning tomorrow. I want to urge you to consider joining this group if you're at all interested in the climate system. It got off to a kind of a rough start, but now this group is very energetic with lots of young people, lots of interesting discussions, ideas, and I think it's a really terrific thing that APS has done by creating this topical group on the physics of climate. So I hope you'll all join. So I'd like to end by just noting that nowadays, when we hear the word climate, when we think about climate change, and we think about all the problems that are associated with it. But I think it's helpful to take a step back and simply admire the beauty of the climate system, of which I've only touched on a few aspects, but there are many of them. So we can gain a greater appreciation of our planet's climate by thinking about it from the perspective of physics. And this greater appreciation, I hope, will translate into a greater desire to understand it more deeply and perhaps solve some of the many pressing problems that face us. Thank you.
Thank you so much. Plenty of time for questions. Again, don't feel shy. Please come up. Or we could get started with, I think there's a virtual one.
The question is there a topological invariant analogous to the Chern number in Earth's atmosphere? If so, what does it tell you physically?
Right. So I avoided talking about the Chern number because the Chern number is properly defined on compact spaces like a Brillouin zone. And when we are dealing with a fluid system, we don't have a Brillouin zone. But in some cases, we are actually able to define a Chern number, or at least a difference of a Chern number, and that's what we did in our 2017 paper. The difference of the Chern number between the northern and southern hemispheres of the Earth for the shallow water equations is 2, and that gives us a prediction that there are these two waves, the Kelvin wave and the Unai wave. But in other situations, more general situations, then I think it's useful to move away from the Chern number because it really is best suited for these compact spaces. And here we're dealing with a non-compact space.
Others? So maybe I'll ask a question which, oh, sorry, please, yes.
Hello, thank you for the beautiful talk. At some point you showed a worldwide picture of the altimetry, I think you call it laser altimetry of the Kelvin wave. Can you explain how that was measured?
Right, so that's by satellite. And of course, the ocean is undergoing oscillations of all sorts of different types. There's a high-frequency tidal oscillation, and that's been filtered out to just show us this lower frequency oscillation associated with the Kelvin wave. But there's a satellite that's literally measuring the altitude, the height of the sea surface.
So there is only one satellite and measuring laser and reflection?
The satellite's going around, so it's covering the Earth rapidly. And on the time scale of this wave, which was on the order of months, then it's able to reproduce this global feature. There's also measurements from ocean buoys. There's a whole network, thousands of these instrumented buoys that are out and measuring the temperature profile of the ocean. By complementary information also showing this wave.
Yeah. But sorry, just so I understand, the laser altimetry is done by shooting a laser from the satellite and watching the reflection, the time it takes or something.
Yes.
Amazing. Thanks.
Amazing. Any more? Or is there a question there? Yes, please go ahead.
Hi, thanks for the beautiful talk. So you showed this analog of ARPES. And in the plot that you showed, the intensity from one of these topological modes seems to be very prominent, but the other mode seems to be missing. Is there some intuitive reason for that? Is there some analog of what we call ARPES selection rules?
Yeah, the topological insulator ARPES I showed was actually a time reversal invariant topological insulator. So it had both branches equally weighted, whereas in the case of the Kelvin and Yanai waves, we're in a broken time reversal situation. So there's only right moving modes, so to speak. There's only modes going to the east. Does that answer your question?
But there was a mode in your initial schematic that was connecting these two, and that didn't show up in the later plot that the observations that you showed?
Right. So the observations are, of course, based on where the power is in the signal. And some parts are just not being stimulated enough to yield a large enough signal to show up in that plot.
Wonderful. So let's thank Brad again for this lovely talk. So in our concluding Kavli Symposium talk, Reaching the Scale of the Entire Universe, we have Professor Gabriela Gonzalez from Louisiana State University, who is renowned as the spokesperson for the LIGO scientific collaboration between 2011 and 2017. This period forms a landmark in the history of physics when Gabby and colleagues shook the scientific world with the announcement of the first direct detection of gravitational waves, which were produced by the cosmic dance and merger of two black holes. I should add that the discovery also struck a deep personal chord, thanks to my black hole physicist father, who had dreamed of this discovery detection all my life and lived to see the announcement. Since then, Gabby and her extended astrophysics community have enhanced our understanding of the universe in leaps and bounds, contributing to multi-messenger astronomy in unimaginable ways through gravitational wave detection. Befitting for the finale, for the theme of this symposium, Gabby will share the wondrous discoveries being made all the way from subatomic to stellar mergers to distant galaxies. Gabby, please.
Thank you. Thank you for such a nice introduction, and thank you for inviting me to be here. This is going to talk, well, can we go back to the first slide? Didn't touch anything. Okay. We are going to talk about a different scale, but I'm going to go back to the very small scales too. I want to tell you about different kinds of gravity waves. We call these gravitational waves to distinguish them from your gravity waves. And it's, like it's been said, we have learned a lot in just a few years. But we have been working on this for decades. So let me start with just some basic math, and I won't do a lot of math. Let's see if I can go back. So let's start with Einstein's equations. Einstein's equations have a lot of difficult math, but hidden in what we call a very simple equation that has Einstein tensor, which is built out of non-linear combinations of derivatives of the space-time metric. How do we measure distances and how do we measure times? So all of that is encoded in this tensor, and that is equal to constants times the stress energy tensor that tells us where the matter is and how it is moving. So according to this equation, the matter tells the metric how to curve, but the metric tells the matter how to move. And that's why there is this interaction, symbiotic interaction. Now, in Maxwell's equations, as you might remember, if you set source is equal to 0, you get a wave equation. With Einstein's equations, things are not so easy, and he actually did this just a year later after publishing his theory of general relativity. And I hope I can make this work. And if you set the source is equal to 0, you don't get a wave equation, but you get a wave equation if you assume that the metric is going to be the flat space-time metric, the one that we all used in physics, in physics homeworks in graduate school, plus a very small perturbation. And you might remember that Minkowski metric is, I keep doing this. Minkowski metric has in dimensionless units, because we use CT, X, Y, and Z, we have -1, 1, 1. So it's a dimensionless perturbation that is measured as a distortion in distance divided by distance. So what we get then is, to first order, a wave equation for this perturbation. And that's a math of gravitational waves. So we do get a wave equation. It describes a transverse wave. It's a quadrupolar wave, meaning that distances are going to change in two different directions. If these directions get longer, these are shorter. But there are two polarizations that I can't get to show. One polarization has the two ellipses forming an X. The other polarization has the two ellipses forming an X. But what's important is that distances change in a quadrupolar way. Because of that, one can think that interferometers that measure differences in distance are the natural way to measure this. Now, what Einstein did in 1916 is to think about what produces these gravitational waves, and this is the source equation, that those perturbations are produced by mass quadrupoles. So you need a non-spherical distribution of mass that's being accelerated. There are two time derivatives there. And unfortunately, there are these constants in here. There is Newton's constant, because this is gravity, and there's a speed of light to the 4th power. So that's what makes the effect of these disturbances so tiny, so much that even he had some words in his paper suggesting that these things wouldn't be measured. He didn't literally say that, but something like that. So we did measure them, as you know, and what we measured were gravitational waves produced by two black holes orbiting in a galaxy far, far away, a long, long time ago. And those disturbances were tiny. They are measured as a fraction, and that fraction was 10 to the minus 21. That's like comparing a hair width to the distance to the nearest star, not to the sun, but the nearest star farther away. So these are small distances, and I want to tell you what we measured and how we measured them. And of course, you know, or you probably have heard, that we have measured that from coalescing black holes. And we know a lot about seeing black holes. Black holes are black, so there is no light coming out of black holes because there's nothing that can come out of black holes. But we can see them if there are things around them. And there's a movie in here. I don't know if you can advance it, please. Not the slides, the movie, the previous movie. Yes. That should be a movie. It's not. Well, if not, you probably have seen this movie. This is a black hole at the center of our galaxy, which we cannot see. There are strong X-rays emissions, but they are not coming from the black hole itself. But there are other stars that are moving around them. And from the trajectory of those stars, we can tell that there is a black hole, and we can measure the mass of that black hole. And the mass of that black hole is about 4 million solar masses, which might seem like a lot, but in fact, our galaxy has a not so big black hole at the center. We think now, astronomers think now, that there are massive black holes at the center of every galaxy, and ours is kind of small. And this received the Nobel Prize in 2020, just less than 3 years ago. And it was very nice to see a theorist, Roger Penrose, who did a lot of the theory of black holes, and 2 experimentalists that measured these ones, including Reinhard Genzel and Andrea Ghez. So I want to tell you about gravitational waves of black holes, and I want to tell you that if you have 2 black holes, like I was saying, then there is no light emitted, because now there are 2 black holes. So how do we see them? And what we like to say is that we can hear them, because we can measure the gravitational waves that they produce. And this is a numerical relativity simulation that's showing some representation of the geometry near the black holes. And these are distortions of distances very, very far from the black holes, here on Earth, for example. So as the black holes are rotating around each other, then space-time is expanding and contracting in a quadrupolar way. And as the black holes get closer and closer, because these gravitational waves are carrying energy away, so they are getting closer, they are orbiting faster. That was Kepler's law. Here the movie slows down. The black holes are moving at about half the speed of light until they merge. And they merge into a single black hole, and then there is a single black hole rotating at the center, but that does not produce gravitational waves because it doesn't have a mass quadrupole moment. Those gravitational waves had been produced for who knows how long, since the black holes met each other. So they were being produced for millions of years, but they are not produced anymore after the merger. But those gravitational waves are traveling through the universe, and because the distortions they produce are so small, it's like they are not interacting. You can think them about neutrinos. Neutrinos travel through Earth, and we don't feel them because they interact very weakly. That's the same thing with these gravitational waves. But this is what we want to measure. And that stretching and compressing of the light, that is a part of 10 to the 1. One part in 10 to the 21. So it's a very, very small quantity that we want to measure with an interferometer, and you all remember how an interferometer works, but I can't resist showing this movie. Can we play the movie? So we have a laser, we split it in 2, and if the distances are changing, then the interference pattern shows a different amount of light at the output. The laser is, of course, an electromagnetic wave, and what really matters in this case is that if these 2 distances are the same, the interference at the output is destructive. So we have no light coming out of the interferometer. Of course, all the light is going back to the laser. There's no energy lost. But if the distances are changing, then we can have more light, less light, more light, less light. So just putting a photodiode at the output and measuring how much light we have translating that into interference, we can measure gravitational waves. Of course, we have to make them big. Remember that Einstein's prediction from the sources is for the delta L over L. So if we make the baseline longer, then we make the disturbance larger. So these interferometers are not in a lab. They're not in an optical table. They are actually very long as taxpayers can afford. And and there are two in the US, LIGO interferometers. LIGO stands for Laser Interferometer Gravitational Wave Observatory. There is one in Livingston, Louisiana, near where I live, another in Hanford, Washington. They are 4 kilometers on the side. You all know the metric system, right? So that's very, very long. We work together with a 600 meter, tiny, not tiny, but 600, much shorter detector, 600 meters long in Germany. These are operated by the LIGO Scientific Collaboration that has about 1,000 people, well, 1,500 now, all over the world. We work together with the Virgo collaboration, that's a mostly European collaboration that operates a 3-kilometer detector in the beautiful Tuscany region near Pisa. I love visiting them. And there's one now in Japan, in the Kamioka mine, that's also 3 kilometers long, and there's one in planning in India. So this is a worldwide enterprise, and it's going really well. So this is what we measured, and it was a huge surprise. Now let me tell you a bit about the history of this. We actually not, I wasn't there, but in the 70s, people like Ray Weiss and Kip Thorne had thought about using interferometers to measure gravitational waves. They realized that they had to be long. They realized they were going to be expensive. So they designed, had conceptual designs to see what kind of sensitivity they could have. And it took about 20 years for these to be funded, for prototypes and R&D to be done. And in the 90s, the LIGO observatories began to be built. The Virgo observatory began to be built about the same time. We operated an initial generation of LIGO detectors in the 2000s. And we showed that technology worked, but we had to make the technology even better. So we had already in mind, and that had been proposed from the beginning, a second generation of technology that I'll tell you about. So that was installed in 2010. And in 2014, we had it more or less working, not at the sensitivity we wanted. We had thought we were going to take data for a few months in 2015, 2016, just as a test run. Before we had that test run, on September 14 of 2015, we saw this. Actually, a computer saw it because we had computer codes looking at the data to tell us whether there was something in there. And we were just trying these test codes because we were not quite running yet. And what I'm showing you in here is in blue, the signal in the photodiode in the Livingston detector. And this is noise. That's what we usually see. We don't see a flat line. We see noise. But then there is a wavy signal that grows in amplitude and frequency, like what you expect of two objects orbiting faster and faster, and then back to noise. And 3,000 kilometers away, the photodiode in Hanford, not exactly at the same time, but 7 milliseconds later, saw the same thing. Not the same noise, but the same signal. And this was incredible. Incredible, not just because it was the first gravitational wave, but also because if you look at the frequency, notice here is a time scale, this is a fraction of a second. If you look at the frequency of this signal, this was consistent with black holes of about 30 solar masses that had not been seen before. There were no black holes with other stars orbiting around of that size. And if you look at the amplitude, that was 10 to the minus 21. From that, we can read the distance, and that was more than 1 billion light years away. So this was huge, not just as a physics discovery, but as an astronomy discovery. We had to be sure, so we took some time to take data so we could have statistics of the noise, which we didn't, because this was the first time we were operating this new instrument. And everything went well. It was very stressful months, but we did it. And in 2016, just a bit over 7 years ago, we could tell the world, and maybe some of you were watching that, we did it. And it was actually a really, really nice press conference. I had the honor to be there because I was at that time the spokesperson for the LIGO Scientific Collaboration, which is a rotating elected position. Ray Wise and Kip Thorne, these two pioneers who had started thinking about this in the 70s, were there. And Dave Wrightsey, the executive director of the LIGO Laboratory, and Franz Cordova, the director at the time of the National Science Foundation. But it was a really, really nice coincidence because that February 11 is also the day celebrated every year as the International Day of Women and Girls in Science. And there we were, 2 women among 5 scientists. Not the actual percentage that we have, but the one we would like to have. So that was a cover that we published. We actually had sent this paper for review before we made the announcement. We wanted referee reports, and we did. And we made the PRL server crash because everybody wanted to read that paper the same day, the same time. It was authored by the LIGO Scientific Collaboration and the Virgo Collaboration. Let me go back to that. It was authored by 1,000 authors, not just from LIGO collaboration, but also from the Virgo collaboration, because we were working all together. And we like to say that we could hear, I like to say that we could hear the music of the universe here, because we were not seeing electromagnetic waves, we were not seeing light. Of course, these are not sound waves either, but it's digital signal. You can put it on a speaker, so that's what we did. If you look at this is a time frequency diagram. This is the frequency of the signal in Livingston and in Hanford. Hanford has less noise, so it had more signal to noise. And you can see that the amplitude is getting larger, the signal is getting brighter, but the frequency is also getting higher. But you can look at these frequencies, and there's probably some musicians here who can tell these are actually very low notes. So it doesn't sound really nice. So what we did, what I'm going to make you listen to, I hope the sound works, is first the signal, the actual signal, just put on a speaker, and you'll hear twice, and it sounds like a very low signal. So we said, well, if astronomers paint the infrared in red and the ultraviolet in blue, we'll add 400 hertz to the signal. And that's what you will hear. Let's see if the sound works. So the first one is the actual signal. It sounds like a heartbeat. It's slow, but it's just one signal. It's twice, just for you to hear it. We love it. Actually, we danced to that music. We did. There's a book that I and 2 other collaborators have just published. It just appeared a few days ago, and it's called The Sounds of the Cosmos. I wanted to go to the next slide. This earned the Nobel Prize in 2017 for Ray Wise, Kip Thorne, and Barry Barish, who had been a very efficient executive director at some difficult times of the project. What we liked is that their affiliations were listed in the Nobel Foundation press release as LIGO-Virgo collaboration. So we all felt like Nobel winners. That was 2015. We took data for 3 months, and we saw 3 signals. The others, they look a bit dimmer, but actually this one has as much signal-to-noise ratio as this one because it's longer. It was produced by smaller black holes. And then in 2016, we began taking data again. For the last few months, for the last month, actually, we took data with Virgo, and we had seen 10 black hole signals, and on August 17, 2017, we saw something different. We saw a much, much longer signal. Notice that here, this is half a second. This is now tens of seconds, which means that these objects, these compact objects, were a lot smaller, as smaller as neutron stars, maybe small black holes. We cannot tell. Unless we see the signal at the merger, we cannot distinguish between a black hole and a neutron star. They look like compact objects. But if these are neutron stars, then when they collide, they do emit light. So these could be seen and not just heard. And that's what happened. It turned out that we were taking data, like I said, with LIGO, with the 2 LIGO detectors and the Virgo detector. And there were gamma ray satellites, Fermi and Integral, that are looking for gamma ray bursts that would be emitted by this collision of neutron stars. And there was an alert from the Fermi satellite at almost the same time than the LIGO and Virgo signals. All 3 detectors could see this, could analyze this signal. And again, I'm going to show you, to make you hear the sound, but now not just of the gravitational wave detectors, actually the waveform, not the actual signal, and of the Fermi detector. Oh, there's no sound here. Well, there was sound, but can we do that again? I just want to see the last image of this. There it is. So that's a much longer signal. These are just the last few seconds. That's a coalescence time, and that was a gamma ray burst. That gamma ray burst was actually not that big. Nobody would have paid attention to that gamma ray burst if it hadn't happened so close to the merger that we saw with gravitational wave detectors. And with 3 gravitational wave detectors, now we could tell astronomers, because we could triangulate. With 2 detectors, you cannot, but with 3, you can triangulate. And we told astronomers, go and look there. And to us, there looked like a small place. Astronomers said, well, that's a huge area. It's not that big, but it had, at the distance that we could tell this event had happened, that was 130 million light years, a lot closer than the black holes, there were about 40 galaxies. So astronomers began looking galaxy by galaxy, and they found one galaxy in which there had been nothing there, and then there was a blue spot that became red, that went away, and 10 days later, from the same spot, from the same galaxy, there were X-rays and radio waves coming. So we have a lot of multi-messenger observation of this, and we can have the movie. And by we, I mean NASA, which is the Hollywood of physics, or at least of astronomy. I know, actually, there have been very beautiful movies made, shown in the previous talks, but this is the NASA movie of this event. So there are 2 neutron stars. Oops. There are 2 neutron stars that are going to be producing gravitational waves. Yes, thank you. And they are going to merge. When they merge, they produce a collimated gamma ray burst. And then there is an isotropic explosion that produces light, and then there's a shock wave with the environment that produces the X-rays and the So we had the whole information there. This was amazing. And in fact, it helps to explain some of the atoms, not the atoms that people in this conference in general talk about, which are usually manipulated by humans, but how are the atoms originated in nature? You probably know much better than I do the periodic table. And you might remember that helium and hydrogen especially, and a little bit of helium, were the elements produced in the early universe. And then the stars took over. Stars began producing heavier elements up to iron, because iron is more stable, and then they produce very, very little of heavier elements. So these elements are produced in stars, but these, including gold and platinum, don't know. People didn't know. And people thought that supernova explosions that have a lot of energy to make atoms collide would produce these heavier elements, but they weren't enough. So neutron star mergers are the next candidate. Nobody had seen a neutron star merger until now. Well, until 2017. Okay, so I have a lot to say in 5 minutes, so let me rush through it. This is what we knew about masses of neutron star and masses of what we call stellar black holes, black holes that are produced not at the center of galaxies, but by supernova explosions. And you can see that black holes are between 5 and 20 solar masses, neutron stars between 1 and 2 solar masses. This is what we know now from our signals. We have measured now 90, that's 90 signals. These are the masses of the neutron stars and black holes that we know from radio astronomy and X-ray astronomy, and this is what we know from our observations. We have taken 3 observing runs with Virgo. We are going to start taking another one, and I did want to take some time to tell you about the technology in here. So let me rush through this, but I hope I get many questions. When we talk about the noise in our detectors, what is it that limits the astrophysics, the discoveries we can make? We actually like to plot the noise, and this is the projected noise, what we think we should have, as a function of frequency. And you can see that around 100 hertz is our most sensitive frequency, and that's a strain, that's delta L over L of about 10 to the minus 23, although this is density in frequency, so it's per root hertz. At low frequencies, we are limited by, different kinds of noises. At these frequencies, at the middle frequencies, we are limited by something that all of you could help us with, which is thermal noise. That's a Brownian motion of our mirrors. And that you would say, well, you have to make it cooler because it's KT. That is actually very difficult because we have hundreds of kilowatts of laser light in the arms being absorbed by the mirrors. So what we actually do is have that thermal noise, that KT, being very, very concentrated on the resonances of the system. That's a fluctuation dissipation theorem. That was part of my PhD thesis. So the less energy losses we have in the system, the more concentrated the noise is at those frequencies. And the one that has been resisting this effort to reduce the losses, it's the optical coatings we have to make on the mirrors. We have dielectric coatings, and the usual coatings for that have too much energy loss. Well, they don't have a lot. So there's a lot of R&D to find ways to coat the mirrors, dielectric coatings that have less thermal noise. At low frequencies, we are limited by what I call gravitational noise or seismic noise. Let me see if I can get there. And at high frequencies, now I went too far. At high frequencies, we are limited by the quantum noise in the light. That's because it's a laser. Laser is made out of photons. We count photons. We, of course, have a statistical error. We have learned to squeeze that statistical error. We actually, instead of measuring vacuum, destructive interference at the output of the interferometer, we inject a squeezed vacuum. That is the squeezing that we do. And in fact, we are now squeezing in phase at high frequencies and in amplitude at low frequencies, because if you squeeze in one direction, you get more noise in the other. That squeezing technique actually earned a Keithley APS award 10 years ago, now in 2013, by 3 scientists, Mavalvala, McClelland, and Schnabel, from the US, Australia, and Germany, showing again international collaboration. So that's the noise. This is the actual device. That's a laser traveling in vacuum. That's ultra high vacuum. That's a high power laser. We are using now almost 100 watts of laser. The mirrors are not just mirrors on mirror holders. They are mirrors hanging in quadruple suspensions, hanging from a seismic isolation system, all of that in vacuum. These are the mirrors with the dielectric coatings. The mirrors themselves are also very, very low noise. And it's a very, very complicated system. It's not just a Michelson interferometer. Trying to go to the next one. It's actually, and again, I'm just amaze you with the keywords. It's a dual recycle Fabry-Perot Michelson interferometer. We make light go back and forth in the 4-kilometer arms. We have recycling mirrors at the input and at the output. We have an output mode cleaner. And all of that just to measure noise that we try to make as small as we can. We have lots and lots of feedback control systems. Well, I might take longer to finish the talk if I cannot advance. Maybe I'm not there. That's a noise. We actually have lots of feedback control system to keep all these optical cavities in resonance. And I have a nice picture here of the control room. That's usually our favorite room. That's the control room in Livingston. That's the control room in Hanford. You would think that she is celebrating a gravitational wave discovery. She is celebrating the first time that the Hanford interferometer could be locked, could be operated in 2014. So these are very complex instruments, and I'm almost done. This is again that power spectral density, but now this is not the design. This is the reality. We want to be down here. We don't put that black line, but we want to be down here. We were here in the first observing run. In the second observing run, we reduce the noise at these frequencies. In the third observing run, we reduce the noise here using more power, more photons, and squeezing. That's how important it is. And we want to do even better. We can measure, we can translate these curves into distances to which we can measure mergers of neutron stars. Can you advance? There, thank you. So in the first observing run, when we had the first discovery in 2015, 2016, we could measure neutron star mergers up to, well, a bit farther, but in average, about 80 megaparsecs. We progressed to a record of 140 megaparsecs in our third observing run with Virgo. CAGRA also began being operational at a lower level. We are going to begin taking data again in May, very, very shortly, and we are going to keep improving our sensitivity, but there is a limit of what we can do in the current facilities, so we have dreams, and we hope that you, taxpayers, help us. And that is to build a next generation ground-based detectors. Those would be longer detectors. There's an Einstein telescope concept, a European concept, 10 kilometers on the side, underground, cryogenic. There is more land in the US. There's a concept that would be 40 kilometers long overground at room temperature, although it could be improved. And that would let us see many more mergers of neutron stars with the detail of the nuclear astrophysics at the very end. So we could be doing accelerator physics with neutron stars. We would be able to see all the black holes. Let me go back. All the black holes that were born in the universe, that merged in the universe, maybe there were primordial black holes. We would see those if those existed. So that's our dream. That's what we are. Those are the concepts we have now. Of course, from concept to reality, it takes decades. So that's why we need to start early. And let me just finish saying that we are working, everything I've told you is on one little corner of the gravitational wave spectrum. Black holes are larger, especially the ones that live at the center of the galaxies, and those have longer wavelengths. Those mergers have longer wavelengths. White dwarfs are larger stars. They would have longer wavelengths. So there is a space detector that's going to measure those. That's LISA, that's going to launch in the 2030s. The supermassive black holes need galactic scales interferometers, and those can be done using the radio signals from pulsars as a galactic interferometer. And the early universe, that's the most difficult one. For that one, we won't be able to do interferometry unless it's really unexpectedly big. So that could be seen as polarization in the cosmic microwave background. All kinds of different instruments to hear the orchestra of the universe. So that's it. Thank you. And this is just the beginning.
Wonderful. Thank you so much. That was beautiful. Yes, we do have time for some questions, John.
So a quick question. Now that you're collecting many binary systems, we must be learning more about the evolution of the universe. What new are we learning? What unexpected has come out from the frequency and distribution of these mergers that you're finding?
Well, let me say that that's a very good question, but on astronomical scales, we are still seeing only the local universe. We're not doing cosmology yet, because these black holes, as far as they look to me as a physicist, they are closed for astronomers. We don't measure them in redshifts yet. However, we are learning a lot about the mass distribution of black holes. And there are and the spins, how fast they spin. And there are lots of questions on how did they form. There seems to be a gap around 30 solar masses. Why? So, of course, with 90 detections, we have some statistics, but it's not a lot. So that's what we are going to be doing. We are going to be taking 18 months of data beginning in May.
So we have, let's keep it to the 3 there, and we're good with the virtual, I think, yeah? Okay, so we'll just keep it to you and you and you. So please, go ahead.
In order to interpret the signal from the gravitational wave detector, is it necessary to compare the waveform with a database of simulated events? And does that, if so, does that limit what you can detect to what somebody has thought of simulating?
Well, actually, not all of these are numerical simulations because they are very, very expensive. So we have phenomenological approximations to those numerical relativity. The more simulations we have, the better our approximations will be. But we use now about a database, a template bank of about 200,000 templates. So it's a huge bank, yes.
So one of the first videos you showed made me think that after the black hole merger, there's no signal. During the merger, you have this chirp with an amplitude that is larger. That's the one you detect. Before, you have a very low signal, very regular amplitude oscillation. Am I right to think that that low signal is below the noise, so you can measure it?
That's right. If you remember my noise curve, it has very high noise at low frequencies.
Right.
So until the orbital frequency, and the gravitational wave frequency is twice the orbital frequency. So until the orbital frequency or the gravitational wave frequency enters our sensitive band, we cannot see it. And that's why we see just the last part before the merger.
So my real question would be then, that signal that comes before is very small, but also very well phase locked probably. So can you average it out and actually see it anyway?
Not with our ground-based detectors. We also dream with LISA that LISA is going to see these much bigger black holes, but maybe there are some intermediate black holes where LISA will see that almost constant phase signal and we will see the merger. That would be amazing.
Thank you.
Hi, thanks for the fascinating talk. So my question is, what is the theoretical possibility that black holes are an exit portal for this computer simulation that we live in?
That black holes are what, sorry?
An exit portal for this computer simulation that we live in.
You tell me. No, we don't. Simulations, like I said, are very good. We can compare them. We use simulations, we use the numerical relativity simulations to test Einstein's theory. Now that we know we have a signal, we can estimate the parameters, and now we can subtract the simulation from our parameters to see if the signal is really consistent with general relativity's predictions. And we haven't found anything out of the ordinary yet.
Thank you, Gabby, so much. Thank you. Let's thank Gabby again.
Thank you.
And so our Kavli Symposium journey comes to a close with its grand sweeping view of phenomena traversing from now even subatomic all the way to the cosmic, punctuated by those beautiful celestial fireworks. Deep gratitude for all four of you for this awe-inspiring experience. Let's just thank all our Kavli speakers again.